Clustering is all about grouping similar data points together. In k-means, we decide which points belong to which cluster by measuring how close they are to the cluster centers, the centroids. But here's the key. The definition of close depends entirely on the distance metric we use. Technically, standard k-means relies on Euclidean distance because its math assumes straight-line geometry. But conceptually, we can explore how using other distance measures, or modified k-means variants, changes the shape of our clusters. Today, we'll explore 5 popular distance metrics and see how each one shapes the clusters in k-means: Euclidean, Manhattan, cosine, Minkowski, and Mahalanobis. The Euclidean distance is the most familiar. It's the straight-line distance between 2 points, like measuring with a ruler. In k-means, using Euclidean distance means the algorithm favors circular clusters, where each point is assigned to the nearest center in terms of geometric distance. This works well when all features have similar scales and when clusters are roughly spherical. For example, imagine we have a simple two-dimensional dataset with points representing houses. One feature is the size of the house in square meters, and the other is its distance from the city center. We want to cluster these houses into 3 groups: small urban homes, medium suburban houses, and large countryside properties. When we use Euclidean distance, each house is assigned to the nearest cluster center based on the straight-line distance between its coordinates. On the plot, you'll see each cluster forming smooth, circular regions around its centroid. Points on the edge of a circle are exactly the same Euclidean distance away from that center as any other point along that contour. Because Euclidean distance treats all directions and scales equally, the clusters appear round and evenly spaced, like bubbles. But if one feature had a much larger numeric range than the other, say size measured in thousands while distance is just a few kilometers, the larger scale feature would dominate and the circles would stretch or distort. That's why we usually normalize or scale features before using Euclidean distance. Next, the Manhattan distance. Imagine you're driving through city blocks. You can only move horizontally or vertically, never diagonally. So instead of measuring the shortest straight line, we add up the steps along each axis. In k-means, this changes circular boundaries into diamond shapes. Manhattan distance often makes the algorithm less sensitive to outliers and better for data with distinct axes. For example, imagine we're analyzing delivery routes across a grid-like city. Each point represents a delivery location, and the centroid represents a warehouse. A truck can't cut diagonally across buildings. It must follow the roads. The Manhattan distance adds up the total travel in the x and y directions. In k-means, this means our cluster boundaries form diamond shapes instead of circles. Each point is grouped by how far it would have to travel along the grid, not by the shortest straight path. This can make the clustering more robust when your features change independently or when data has strong axis alignment, just like city blocks. Cosine distance looks at the angle between 2 points instead of their straight line distance. If 2 points point in the same direction from the origin, even if they're far apart, they're considered similar. This metric is especially useful in text and document clustering, where it's the direction of the features, not their magnitude, that matters. Let's say each data point represents a document, and each feature represents the frequency of a certain word. 2 documents might have very different word counts, but if the proportions of words are similar, they'll point in nearly the same direction in feature space. Cosine distance measures that angle between directions. The smaller the angle, the more similar the documents. In k-means, clusters form like slices of a pie, each capturing a distinct direction. It's perfect for text analysis, recommendation systems, and any case where magnitude doesn't matter, just orientation. Minkowski distance is a flexible, generalized form of both Euclidean and Manhattan. It adds a parameter, usually called p, that controls how distances are calculated. When p equals 1, we get the Manhattan distance. When p equals 2, it becomes Euclidean. By adjusting p, we can move smoothly between these shapes and fine-tune how k-means perceives closeness. For example, imagine we're clustering customer behavior, how often they buy and how much they spend. By tuning the Minkowski parameter, we can make clusters more square-like or more round, depending on which patterns we want to emphasize. This flexibility makes Minkowski a bridge between different distance perspectives. The Mahalanobis distance takes things one step further. It considers not just how far points are, but also how the data spreads and how features relate to each other. If your data is stretched or tilted along certain directions, Mahalanobis adapts to that. It scales distances based on variance and correlation, allowing clusters to form along the data's true shape. Imagine you're analyzing students based on math and physics scores. Usually, these subjects are correlated. Students good at one tend to be good at the other. Mahalanobis distance accounts for that correlation, forming clusters that follow the real direction of the data, even if it's tilted. In k-means, this means clusters aren't just circular. They can be elliptical, aligning perfectly with the underlying patterns. Let's put it all together. Euclidean forms round clusters using straight-line distances. Manhattan creates diamonds that follow the grid. Cosine groups points by direction, not by scale. Minkowski connects them through a flexible distance parameter, and Mahalanobis adapts to the data's shape and correlation. Each metric tells k-means a different story about what it means to be close. The best choice depends on your data and your goal. So next time you run k-means, remember, distance defines the shape of your understanding.